When archaeologists study fossils, they use a technique called carbon-14 dating, which uses exponential functions. Hi, my name is Tom Atwater, and in today's lesson, we will be exploring exponential growth and decay. Let's start off with a definition. Let A be a positive real number other than 1. Then the function f of x equals a raised to the power x is the exponential function with base a. Let's sketch the graph of two exponential functions. Y equals 2 to the positive x and y equals 2 to the negative x. What I want you to notice is that for this graph, we have a domain which is from negative infinity to positive infinity. The graph is increasing, and the range for this particular function is from not inclusive of 0 up to infinity. The x-axis is a horizontal asymptote. Well, what about the graph of y equals negative 2 to the x? This graph does this. And again, the domain goes from negative infinity to positive infinity. The range, not inclusive of 0, because again, the x-axis is a horizontal asymptote up through infinity. But this time, the graph is decreasing. And this would be an example of exponential decay. We can generalize these concepts as follows. The function y equals k times a to the x, where k is positive, is a model for exponential growth if a is greater than 1. And it's a model for exponential decay if a is between 0 and 1. Well, let's take a look at an example in the form of an application. The population of Knoxville is 500,000 and is increasing at a rate of 3.75% each year. We want to know approximately when will the population reach 1 million. So let's use the following model for the growth. The population is equal to the initial population times the quantity 1 plus r raised to the power t. R in this case represents the growth rate, the 3.75%, and the t in this case represents years. So what we need to do is plug in the information that we were given, which is we want to know when will the population reach, or approximately when will it reach 1 million. Okay, so we take 1 million, and that's going to equal 500,000. 1 plus 0.0375 raised to the t. And now what we do, of course, the 1 million divided by 500,000 gives us 2, and that's going to equal 1 plus 0.0375 raised to the t. Now you can use your calculator function to solve this particular problem, and what you'll get is that it's at approximately right after 19 years, and the population will have reached 1 million. Well, let's do another example. Let's take the example about half-life. The half-life of phosphorus-32 is about 14 days. There are 6.6 grams present initially. First, express the amount of phosphorus-32 remaining as a function of time t, and second, when will there be 1 gram remaining? So the formula that we can use for half-life is that the amount present at any particular time, t, is equal to the initial amount and then the 0.5 raised to the exponent of t divided by the half-life of t. So in this example, what we would set up is that the amount we want is 1 gram. We started with 6.6 grams. We have 0.5, and we're going to raise that to the t, which is how many days it will take for there to be only 1 gram, divided by 14, which is the half-life. Now, one of the ways you can solve this would be to use the calculator, in which you plug in and make this equal to y1 in the equations window. And then what happens is you tell it to graph that, and what you'll see is this graph right here. And what will happen is when you ask it to solve for the intersection of the line y equals 1, which is this horizontal line, and the graph itself, you can come up with, and you can see it on the graph as I was working it out, that y is just slightly over 1 and x is just slightly under 38, which means that when y is actually equal to 1, we would be just slightly over 38 days, and that's when there would be 1 gram remaining. Okay, next, let's turn our attention to the number e. E is an irrational number that, when used as the base for exponential functions, models natural phenomena very closely. Let's look at its approximate value and how it might be used. We can define e to be the number that f of x is equal to the quantity 1 plus 1 over x raised to the x, and that this approaches as x approaches infinity. The value of e is approximately 2.718281828. One of the places that we can see the usefulness of e is in interest, which is compounded continuously. So let's take a look at that. Interest compounded continuously uses the model y equals p times e raised to the RT, where p is the initial investment, r is the interest rate as a decimal, and t is the time in years. All right, so determine how much time is required for an investment to double in value if the interest is earned at a rate of 6.25% compounded continuously. Our formula for compounded continuously, y equals p times e raised to the RT. We're interested in the amount doubling, which means that when, if our initial amount is p, then we're going to be looking at 2p as being the amount present. So 2p equals p times e raised to the interest rate, which is the 0.0625 times t. Of course, the p's cancel out, and we have the equation that's simply 2 equals e raised to the 0.0625 t. And let's use the calculator to solve this problem. So we would plug in the equation to the equation window, and we would get the graph. Here's the graph y equals 2, the horizontal line. There's the graph of our equation of e raised to the interest rate times t. And what you can see here is we're at a y value very close to 2, the 1.996, which gives us an x value of 11.06. So what it means is that it's just over 11.06 years to double that amount. Well, now it's time for you to try a problem. I want you to determine how much time is required for an investment to double in value if the interest is earned at a rate of 5.25% compounded continuously. So pause the video while you work on this problem. When you are finished, restart the video to check your solution. All right, let's find out how you did on that problem. The formula that I wanted you to use is the same one that we used before, which is y equals p times e to the rt. And once again, you were looking at we wanted p to double. So it would be 2p equals p times e raised to the 0.0525t. And of course, the p's cancel. And so we have 2 is equal to e raised to the 0.0525t. And once again, we can take and plug into your calculator that this would be equal to y sub 1 in your equation editor. This would be equal to y sub 2. And let's take a look at what that printout would yield on the calculator. You would have this graph, which looks similar to what we had before. And this time, we have the y value of 2 and the x value of just over 13.4, which means that it's just over 13.4 years and the money is doubled. If that's the answer you got, then that's great. Okay, in this lesson, we learned about using the letters E as an exponential function for modeling real-world problems in both growth and decay. Be sure to work the exercises that your teacher assigns, and we'll see you next time.